So in this example, we actually have more than two spheres. We have three of them. A is positively charged, B is negatively charged, they are in fixed positions, and C is the charge that's free to move. Based on that, we want the net force on sphere C. What we know is that the charge between B and C will actually be an attractive force because they're oppositely charged, and the force between A and C will be repulsive. So we actually need to calculate both of these forces. So from A to C, we know Q1, we can call that the charge on A. That would be 4.0 times 10 to the minus 6 coulombs. Q2 would be the charge on C, which would be 6.4 times 10 to the negative 6 coulombs. The distance separating these two spheres would be 30.0 centimeters, which would be 0.300 meters. Plugging these into the equation, K, look it up as always, 8.99 times 10 to the 9th. Q1, Q1 is not 6.4 times 10 to the minus 6, it's 4.0 times 10 to the minus 6. Q2 is 6.4 times 10 to the minus 6. R is 0.3, and that is squared. Calculating that out, we'll go to 2 sig figs here. That is 2.6 newtons. And in a question like this, because we are dealing with the overall force, the direction is important. Since this is repulsive and C is the sphere that can move, this force will push C to the right. We also need to calculate the force between B and C. I'll just clear off the page to do that. So from B to C, the charge on B is negative 2.5 times 10 to the minus 7 coulombs. And that negative is just there to indicate that it is actually a negative charge. Q2, charge on C, 6.4 times 10 to the minus 6 coulombs. The distance between B and C would be 10 centimeters, or 0.1 meters, with 3 sig figs. The force from B to C, it's the same equation as before. We'll go straight to plugging things in. K is 8.99 times 10 to the 9th. Q1, negative 2.5 times 10 to the negative 7th coulombs. Q2, 6.4 times 10 to the negative 6 coulombs, divided by 0.1 squared. Calculating that out to 2 sig figs again, we get negative 1.4 newtons. Or we could call that positive 1.4 newtons to the left, since C will be attracted to B. Now the net force on C is just the sum of all the forces. So the force from A to C plus the force from B to C. So from A to C, we had 2.6 newtons to the right. From B to C, we had 1.4 newtons to the left. The issue with this is that we do not have the same direction. We do need to account for that. I'm going to leave everything to the right. So this would turn into subtract 1.4 newtons to the right. So the net force on this would end up being 1.2 newtons to the right.